Hello, my name is Peter Prastakos from MIT, and I will be introducing our new paper on differentially private best subset selection via integer programming. So the problem we're looking at is the best subset selection problem, wherein we're trying to minimize least squares subject to an L2 as well as an L0 constraint, where L0 is the number of non-zeros of the beta feature vector. So this is an important methodological problem of interest in the optimization and statistics communities. And if we just had least squares with the L2 constraint, then we would have a convex problem that can be solved using standard algorithms like projected gradient descent. However, with the introduction of a sparsity constraint, we now have a hard combinatorial problem that is non-convex. And so recent work has involved using mixed integer programming to solve BSS in larger instances. So brief review of definitions. Epsilon delta differentially private algorithm is one such that this equation holds. And in our particular case, delta is set. We will present an algorithm where delta is 0, so it's a pure differentially private algorithm. So as I mentioned, the goal is to find a DP algorithm that is pure, but to find the optimal location of non-zeros in BSS. Current algorithms involve doing convex relaxations, private lasso, Markov chain mixing. And we want to focus on the combinatorial form of the problem because recent work has shown that non-private BSS can have favorable practical and theoretical properties over its convex relaxations under certain settings. So the exponential mechanism from the DP literature is a pure differentially private mechanism. And here capital O is our outcome set and capital R is the scoring function. And in our case, the capital O will be the set of all possible subsets of size S from P. And the objective for each S, the scoring function, will be minimizing the least squares under the restriction of X to the columns where beta is non-zero. So the global sensitivity is defined as in the literature as the max difference for any support and for any two neighboring data sets between the scoring function at the two data sets. And under assumptions of boundedness on the data Y and X, we can then get a bound on the global sensitivity for our particular case. So we will seek to solve a series of mixed integer programs to find the optimal support from 1 up to capital R, where R is some value that we have as input, which is significantly less than P choose S. The goal is then that we have the access to the Rth best supports in sorted order, and then we can use those to essentially approximate the exponential mechanism. So we define our distribution to be proportional to this distribution takes values from 1 up to R plus 1. And if we have a value from 1 up to R, then we would do the same as the exponential mechanism would, set it proportional to this value. And if it's R plus 1 and we lie in the setting of any of the supports essentially that are from R plus 1 up to P choose S, then we do a uniform draw from those supports. And so the main benefit of this mechanism is that we no longer need to sample from a non-uniform distribution with exponentially large support. And we have DP guarantees of pure differential privacy. So our algorithm has shown favorable statistical properties of probability of recovery for different values of S and R, epsilon, the privacy parameter, and S, the scarcity parameter, for varying values of P and N. And so in conclusion, we're presenting a new DP algorithm for variable selection. We're using mixed integer techniques to scale it up and showing good performance for P up to 250. If you're interested, please check out our paper on open review. And thank you very much for watching.